Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Miaki Ishii is a professor of Earth and Planetary Sciences at Harvard University. She received her PhD in geophysics from Harvard in 2003, and after a postdoctoral fellowship at the Scripps Institution of Oceanography, she joined the Harvard faculty. Professor Ishii is especially known for her research on the internal structure of the Earth in an effort to illuminate phenomena such as earthquake patterns and the peculiarities of the Earth's core. Using imaging techniques roughly similar to CAT scans and MRI, she analyzes recordings of seismic energy. From the seismic energy recordings, she develops images of the planet's interior without sending instruments deep into the Earth. Tonight, Professor Ishii explains why these seismological images are particularly valuable. For example, such imaging makes it possible to view the internal structure of the Earth from different angles, and she can obtain a much better idea of earthquakes and other phenomena. Her work represents a great contribution to modern science, and it is a real pleasure to welcome Professor Miaki Ishii.
Thank you.
Welcome.
Thank you for the opportunity to talk to you about what we do, partly, and I'm also going to cover various things that others have also done. So I'll just take you through to the journey to the center of the Earth, if the slides can come up. So what I'm going to do is give you a tour of going from the surface of the Earth down to the center of the Earth, but I'll spend less time near the surface and spend more time as we go deeper down. That is opposite of what most people do. Most people would spend a lot of time closer to the surface. It's more accessible, we have more data, but I think it will be fascinating to see what happens at the center of the Earth as well. So what I'm going to start out with is what we know about the Earth. So here's Earth. It is roughly a sphere with a slightly oblate shape, meaning that it's slightly squished at the top. So if you look at the size of it, we have an average radius of nearly 6,400 kilometers. But the radius is slightly different at the equator and at the poles. So at the poles, it's slightly shorter compared to the equator. Now, we knew about the size of the Earth from about 230 BC. So for a long, long time, we knew what the size of the Earth was. We also knew what the mass of the Earth was. It was discovered in 1798. So we know that the total mass Earth is a very heavy sphere, and the average density is about 5.52 grams per cubic centimeter. So it's roughly a rock. Now, in terms of the internal structure, even though we knew what the size was, what the mass was for a long time, in terms of the internal structure, this is the view from 1663 by Kircher, Mundus Subterraneus. This is a famous drawing showing what happens inside the Earth. So we have the Earth right here, and inside it we have lakes, rivers, fireballs, and so on and so forth. This is obviously an imagination. Now, around the same time, we have been making great progress in science. In 1609, law of planetary motion was presented by Kepler. 1628, blood circulation was discovered by Harvey. 1643, mercury barometer was invented. 1662, ideal gas law explaining how the gases behave was discovered by Boyle. 1675, microorganisms were discovered, these tiny things that do a lot of damage to us and do a lot of good things to us. Speed of light was measured in 1676. Newton's law of motion was discovered in 1687. So it seems like this is the time of great scientific discovery, and yet, in terms of the Earth interior, we're still looking at imagination. So why is that? And I think one of the things that we should consider is how can we learn the interior of the Earth? And once a seismologist was giving a talk at my home university, and one frustrated physics professor stood up and said, why don't you just dig down? So let's consider how much we can dig down. So here's the animation, one of my favorite animations, showing you the deepest hole that we've managed to dig. So here's the animation. Here's the cross-section of the Earth. We're basically cutting through the Earth, and we are trying to find what the deepest hole is. So that's how much we've dug. If I play it again, this is the tiny bit at the top that we managed to dig down, and there are good reasons for it. So this is how far we got it down, 12 kilometers. Now, compared to Mount Everest, which is almost 9 kilometers, we've dug more than that. So this is a huge accomplishment. It took a long time to do that. This was done in Russia at it's called Kola Super Deep Hole. And it's done at Kola Peninsula in Russia. They started drilling on May 24th, 1970. So they set up a huge rig and then started drilling. It took about 13 years to get down to 12 kilometers, or 12,000 meters. After a year, they managed to go down a little bit more, 66 meters. After 5 more years, they got down to 262 meters, or 12 kilometers and 262 meters. So it seems like we were making a very good progress at the beginning, but it slowed down significantly. They wanted to reach down to 15 kilometers depth. However, after trying for 3 more years, they had to abandon. Now, why is it that it's so hard to drill down? It turns out by the time you get down to 12 kilometers, the temperature is about 180 degrees centigrade. So it's way above the boiling point of water. And if you try to even go down furthermore, it's going to get hotter. Now, even though this is a huge accomplishment, 12 kilometers, we've gotten a lot of good samples. We have made great progress in terms of studying the Earth's core. In terms of studying the entire Earth, compared to the radius of the Earth, which is 6,371 kilometers on average, this is less than 0.2%. So we just can't dig down to get there. One of the reasons is temperature. So if we look at the temperature, so on the y-axis, we are plotting the temperature. And on x-axis, we're going from the surface of the Earth to the center of the Earth. And these red bars are showing what the range of temperatures are. We are sitting pretty much at 0 right now. It's 200 or so. And it's going to go up very rapidly to more than 1,000 Kelvin. By the time you get to near the center of the Earth, we are looking at something like 6,000 Kelvin, which is equivalent to the temperature of the sun at the sun's surface. So this is very, very high temperature. And therefore, whatever we send down there has to be able to survive through this intense heat. On top of that, we have pressure effect. We have high temperature, but we also have pressure. So this is a similar plot showing pressure on the y-axis, depth on the x-axis. At the surface, we have atmospheric pressure. So at the Earth's surface, we have some pressure. This is equivalent, if you think of how much weight I should put on my fingertip, it's equivalent to 1 kilogram of weight on my fingertip. Now, the only thing you have to think about is this is pressure, so it's coming in from all directions. So you're going to squeeze my fingertip with however heavy things are. This is what we can live with. This is what our body is supposed to do. But once we get to, let's say, about the center of the Earth, about the midway down, the pressure goes up to about 135 gigapascals. The number doesn't really mean much, but if I convert to equivalent values, it means that we have more than 1,000 tons of material sitting on my fingertips. So my fingertip is not going to survive. So what's happening is we have more than 1 million times pressure acting at the midway through. So in order to keep a void open, to have humans go there or instrument to survive down at these depths, it's very unlikely. Whatever we put there, it's going to be squished and squeezed down, and it won't survive. It's a technical term. I'll call it a technical term. We'll just squeeze it down. and we'll crumple things over. Once we get to the center of the Earth, obviously the pressure is going to go up, and it's going to be equivalent to having more than 3,000 tons of material on my fingertips. So it's very unpractical, if not impossible, to send any material or any probe down to the center of the Earth, let alone look at something very shallow part. 12 kilometers is pretty much our limit. Beyond that, it's too high temperature and high pressure to have the probe survive. Now, therefore, we can't actually go down there to make measurements. There are movies about going to the center of the Earth and so on and so forth, but I hope you have an idea why that's unlikely. That as much as I'd love to have that sort of data, it's not going to happen. Now, let's say you broke your bone. I'm sure someone would have broken a bone at some point in their life. I broke my bone once or twice. Your doctor is not going to open you up to see what's going on inside you. We have non-invasive techniques to find out what goes on inside, and we take advantage of that. So let me give you an example of what happens with medical imaging. Here's an idea of X-ray imaging. If I break a bone, I'll go to my doctor and say, well, I broke a bone. He's probably going to take an X-ray image of me. So what's happening there is we have some sort of energy source, X-ray source, that's sitting here emitting all these energy particles. The particles are going to interact with my target, in this case a hand, and the rays are going to bend or transmit and so on and so forth. And on the other side, I'll have a recording. Now, this is a picture from one of the earliest Röntgen pictures, but what you can see is you can see the inside by analyzing these particles or waves that have interacted with your object. We're going to do exactly the same thing, but we're going to change slightly. In terms of having a source of energy, instead of having an X-ray source here, we're going to have earthquake as energy source. Instead of X-rays traveling through your target, we're going to have seismic waves that are generated from the earthquakes, propagating through the Earth, our target, and our recordings are going to be seismograms recorded around the world. And what our task as seismologists is to decipher these seismograms to come up with the images of the interior, just like I can see my broken bone with the X-ray imaging. So let's look at earthquakes. Here's the distribution of earthquake for 20 years or so, and you can see that they are not evenly distributed, but we have a lot of them. Just today, or in the last 2 weeks or so, we have so many of these earthquakes. The red ones are from today. I took this photo or this picture today around noontime, so it's off by 6 hours or so, but that's all right. You can see that there are a lot of earthquakes. The red circles are from today, orange are from in the last 2 days, and yellow ones are from the last 2 weeks. So you can see that there are plenty of earthquakes for us to study. These earthquakes are going to act as our source, just like the X-ray source, and they're going to generate seismic waves instead of our X-rays. So when you have an earthquake, this is actually a simulation trying to show what happens. So here's our target, our source earthquake, and we are going to see that there are different stations around the world, and the seismograms are going to show up on the top panel. So when the earthquakes happen, they generate seismic waves, and they propagate through the Earth and along the surface of the Earth. So what we are seeing are different types of seismic waves traveling through the Earth. On the right-hand side, the cross-section is showing you where they are going through. And on the left-hand side, you're seeing where they are in terms of surface location. And whenever a wave arrives at a station, that's recorded as wiggles at the seismic station. So on the top panel, you can see all sorts of wiggles, and they correspond to different types of seismic waves that are arriving at a particular station. So we have to use those information to try to come up with the Earth interior. We have a lot of stations. Here is one set of stations that you can see. These are being used to monitor for seismicity. If there's a large earthquake, these instruments would record that and tell us immediately that there was a large earthquake. So these are used for monitoring purposes, but they are also used for research in terms of the Earth interior. We have a lot of stations, and most of these are reporting data in near real time. So we can get access to these data as soon as they become available. Now, using this sort of data set, the earthquakes, the seismic waves that are going through recorded by the network, we can start to improve our picture of the Earth interior. So let's go back to the drawing from 1663. Here's what we had. This is not in color. It's black and white, but it's the same idea. You have rivers, lakes, fireballs, and so on and so forth. By 1903, this is the drawing from 1903, showing you that there are different layers. It's still deformed quite a bit, and there isn't much there, but it's a huge improvement. The reason being that seismometers were discovered in 1880. So from 1880 to 1900, we had some time to collect the data and start to make progress in terms of studying the Earth interior. By 1973, we had a better idea. Previously, in 1903, we had just a single core. But now we have core, multiple layers of core, for example. And even if we go a little bit closer to current time, here's a 1990s view of the Earth. We have color. We are getting better in terms of printing things in color by that time. And you see different layers with different colors. And this has been achieved because we now have a global network of stations that are recording data all the time, and we have access to them. So let me look at the current view of the Earth interior. So here's the cut through into the Earth. We start at the surface. It's somewhere we are very familiar with. At the very top, where we are living, we have oceans and crust. So we have water. 2/3 of the Earth's surface is covered by ocean, and then the rest is the solid crust. Now, the crust is heterogeneous, so you have different regions with different material. Some places you might have sandstone, some places you might have granite. So crust is heterogeneous in terms of lateral dimension. This ocean and crust layer makes up about 1% in terms of Earth volume, so it is tiny. And we have a hard time even getting through the crustal layer. Beneath that, we have solid mantle. This is also heterogeneous as indicated by these colors, blue and red, and I'm going to explain that later on. Beneath the solid mantle, we have liquid outer core. So now we are getting from the mantle to the core, but right beneath the solid mantle, we actually have something that's liquid. And this outer core consists of about 16% by volume. Below that, we have solid inner core. We are not quite sure if it's homogeneous or it has heterogeneities in there, but it's a fairly small sphere sitting at the center of the Earth, about 0.7% by volume. By far, the mantle makes up the most volume. It's 83% by volume. So let me start with the mantle. Let me skip the crust a bit because it's so thin at the surface, and we are kind of familiar with that. Let me take you into the mantle first. Here's the cross-section showing you from the surface of the Earth or top of the mantle to the core mantle boundary. Beneath here we have core, and we are looking at what happens as a function of depth. The blue colors are where the seismic waves are traveling more faster than average, and red are where seismic waves are traveling slower than the average. So you can think of this as a CAT scan image or your X-ray image. Now, what we see is this fast material, which we tend to relate to cold material, because when something is colder, waves travel faster. The cold material is sinking down here. Similarly here. In two different places, we seem to have slabs or cold material going down into the Earth, and this is consistent with our idea of plate tectonics. We think of plate tectonics as convection in the mantle, where the cold plates, the plate that spent some time near the surface being cooled from the top, are going to be recycled back into the Earth interior, down into the mantle, and then eventually they'll make their way up and then come up to the surface. So what you're seeing is this part where the material is sinking down to the core mantle boundary. Now, we have this going on in the mantle, and there's vigorous research going on in terms of how to image this, how to improve the image. We want to focus better. This is somewhat of a blurred image, but if we can focus better, we might be able to see more exciting things. Now, we have the mantle sitting on top of the liquid core. The first question is, why are they separated? Now, at the earliest point in Earth history, we had a fairly vicious environment where the Earth was bombarded by little planetesimals, and we had magma ocean. When you have something mixed with different composition, let's say we are mixing oil and water. Now, the bombarding and melting of material is going to be like this mixing of oil and water, but after a while, they're going to differentiate. The oil is going to float up, and water is going to be sitting below. And that's what's happening in terms of the Earth differentiation. The heavy metals are going to sink to the center, and that's going to make up the core, whereas lighter rocky materials are going to stay at the top. And that's what our mantle is. So in terms of composition, we have what's called silicate mantle, or if you will, rocky mantle, sitting on top of metallic core. The core is made up mostly of iron, with some other things mixed in there. Now, the core can be divided into two. One is the outer core, which is liquid, and the other is the solid inner core. And I'm going to talk a little bit about what happens in the outer core before I get into the inner core. Now, the outer core is liquid. It's hot. So what it's going to likely to do is to convect, just like mantle is convecting. So there will be vigorous convection in the outer core. We are mixing a liquid. We are also mixing a conductive material. Iron conducts electricity, and you're basically moving that around. And in the presence of magnetic field, that's going to actually generate more magnetic field. So the convection in the outer core is actually generating the magnetic field of the Earth. So you probably have seen this sort of magnetic field line drawings where our compass is going to follow the lines and point to the north. The North Pole is actually a South Pole in terms of magnetic poles, and you've probably seen a picture where there's a bar magnet inside the Earth. Now, this magnetic field is generated by the outer core, the convection in the outer core, rather than Earth being a bar magnet. And the consequence of that is actually quite interesting. You can do some numerical simulations where you're trying to recreate the magnetic field of the Earth, and you can draw magnetic field lines, just like this. So the blues are the field lines that are pointing inwards, and red are the field lines going outwards. In other words, the blue is the north our compass is going to point to. Now, it is stable for a while, but if you let it run, it's going to do something strange. It's going to make this more like, look more like a spaghetti diagram, and it's going to even get messier. And sometimes you actually flip the polarity. Now, your North Pole is going to be South Pole, and your South Pole is going to be North Pole. And you can't do that if you have a bar magnet sitting inside the Earth. So this is one consequence of having convection in the outer core, that we are not going to have a magnetic field that is going to be the same all the time. So here, currently, we are sitting in what's called normal epoch. And we have North Pole being North Pole, South Pole being South Pole. And we could have, however, magnetic reversals. And we could end up having the North Pole being our South Pole and South Pole being our North Pole. We have recordings of that. And if we go back in time from current time at the bottom to 5 million years ago, the colors are showing different polarities. The dark colors are the normal polarity, North Pole being North Pole. The whites are when we had magnetic reversals. The South Pole was our North Pole. So we've had this for a long time. We had reversals going back and forth, and we don't quite still understand how often we should have it, whether we are going to go into a reversal right now or we are going to have the normal polarity for a while. This is, again, a vigorous field of research. One thing the magnetic field does for us is to protect us. So the sun is going to emit, sun always emits harmful solar wind. And because these are charged particles, the magnetic field is going to bend their path. So they might want to come directly at us, but the magnetic field is going to divert the energy away from us so that we don't end up with all these solar radiation reaching us. And one consequence of that, you can see that all these charged particles are deflected from the Earth, but they would be coming in through the polar regions, magnetic poles. And one consequence is the spectacular northern lights that we see in the north and south poles. And the reason being that that's where the charged particles are being directed and can arrive into the Earth. And these charged particles are going to interact with the Earth's atmosphere and generate these lights. Now, that's the outer core. So we basically went down to the outer core, and now we want to get into the solid inner core. The mantle core boundary was a chemical compositional boundary. We had different material. One was rocky, one was metallic. The difference between the outer and inner core is the phase. The outer core is liquid, inner core is solid. So it's like water and ice. There isn't much difference in terms of composition. So it's a phase boundary rather than a compositional boundary. The Earth's inner core was discovered by a female Danish seismologist, Inge Lehmann, in 1936. So here is a comparison of the size of the Earth, the Moon, and the inner core. So you can see that the inner core is pretty small. In terms of its radius, it's about 1,200 kilometers in radius. So in comparison, Moon's radius is about 1,700, so it's a little bit smaller. Earth's radius is more than 6,000 kilometers. In terms of mass, it's 9.84 times 10 to the 22 kilograms. It probably is a huge number that we are not very familiar with, but even though it's smaller than the Moon, it's actually heavier than the Moon. And that's because Moon is mostly made up of rocky material, something similar to what the mantle is made out of, whereas inner core is made out of denser material, this metal. And that's why it ends up being heavier even though it's smaller. In terms of the mass, it consists 1.6% of the Earth's entire mass. And it sits at the center of the Earth. Now, we need seismic waves to go through this inner core in order for us to image them. And we have multiple things. So here's one example. This is an earthquake that happened in southern Sumatra in 2004. This is a different one from the one that generated huge tsunamis and devastated region around the Indian Ocean. It's an earlier one from July. And this earthquake generated seismic waves that were recorded in Florida. This is a station in Disney Wilderness Preserve in Florida. Believe it or not, Disney World has a seismic station there. Now, if we make a cross-section of the Earth, how the waves got there is going from the source to the station, through the mantle, through the outer core, and through the mantle again to get to the station, or through the mantle, through the outer core, through the inner core, which is the blue path, through the outer core, through the mantle, and reach the station. And these are going to generate seismic recordings. So these three paths, one going through the top part of the outer core, the dark green, or the one that's going deeper part of the outer core, lighter green, are coming in at this time and that time. So this pulse is the wave that went through the top part of the outer core. This smaller one is the one that went very deep, close to the inner core. And the first one, this very first blue one, is the one that went through the inner core. So if we collect a lot of these data, we can start to learn about the behavior of the inner core. One peculiarity about the inner core is it has what's called anisotropy. So let me explain that. If I collect a lot of inner core observations, so I take this sort of distance, so here's the source, here's my station, and I can collect a lot of these and organize them in such a way that I know which direction the waves are traveling through the inner core. So on this side, I have rays that are traveling east-west, so perpendicular to the Earth rotation axis. On this end, I have waves that are traveling north-south, parallel to the Earth rotation axis. And so that's the x-axis, the orientation of the ray in the inner core. On the y-axis, I'm plotting what's called travel time residual. How was this ray arriving, how late or early is this ray arriving with respect to an average value. If you do that, here's a zero line. The rays that are traveling perpendicular or east-west direction are arriving slightly later than expected, but the rays that are traveling parallel to the rotation axis or in the north-south direction are arriving much earlier. So there's a directional dependence of the seismic wave speed that's giving this sort of signal. Now we can see what happens as a function of depth. We can collect data from this sort of path that's sampling the shallowest part of the inner core, or we can go somewhere deeper, sampling a little bit in the mid part of the inner core, or if we go to the other side of the Earth, if we happen to have source station pair that is on the other side, at the antipodes, we can go right through the center of the inner core. These panels are showing the exact same thing when on the left-hand side you have waves that are traveling in the east-west direction. On the right-hand side you have waves that are traveling in the north-south direction. And we are going from shallowest part of the inner core slightly deeper, 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 deeper until we get to the ones that sample the center of the Earth. Turns out we can model most of this by a fairly straightforward anisotropic model. So the red curves are showing the predictions based upon this simple anisotropy model, and they seem to agree with the data reasonably. There are some scatters, but again, we're dealing with the real data, and therefore we expect some uncertainties. So it seems like the fit is good until we look at the one that's deepest. So let me focus on these two distances. This data set is sampling the top 200, 300 kilometers of the inner core. This one that is basically on the other side of the Earth is sampling the center of the inner core. So if I compare these two, here's the sampling depth of the one from smaller distance range, and here's what this antipodal path, the one that goes through the center of the Earth, is seeing. So here's the one from the shallow inner core. Here's the one from the deeper inner core. And the red curve, again, is the prediction from a simple inner core anisotropy model. And you can see that the one from shallow part of the inner core is matching very well with the predictions. The blue dots with uncertainties are the observations, and red curve is the prediction. On the other hand, one from the other side of the Earth is not agreeing very well. So if I remove the prediction, I see this behavior. Instead of east-west direction being the slowest, it's not. The slowest direction seems to be when it's here. So the anisotropy is changing behavior when it gets close to the center of the Earth. So this suggests that there might be two distinct layers in the inner core. The material might be the same or it might be different. We don't really know, but at least the data suggests that there's some difference. So we can come up with a two-layer inner core model. We have the top part, the bulk inner core. That seems to go well with the fairly simple anisotropic model. And the center shown by the blue would require slowest direction here and fastest here, with fast direction also in the east-west. If I translate in terms of wave speed rather than the travel time residual, we have slowest speed when you are about 45 degrees from the rotation axis, fastest, highest wave speed when you are 90 degrees or parallel to the rotation axis, or you also have somewhat of an intermediate speed when you're traveling in the east-west direction. Now this is fairly distinct from the bulk inner core case, where you have the slowest direction in the east-west direction and fastest direction in the north-south direction. So we've added some complexity to the behavior of the anisotropy. It's also different in terms of the magnitude. The top part is not as strongly anisotropic as the bottom part. The difference in velocity is about 0.2 kilometers per second. So I'm taking this maximum value minus minimum value, it's about 0.2. For the central part, the innermost inner core, we have about 0.8 kilometers per second, so 4 times larger in terms of difference in wave speed, as well as change in the behavior. So if I summarize the two-layer inner core model, we have this sort of scenario. We have the bulk inner core, which makes up most of the inner core, most of the volume. And it has weak anisotropy. The fast direction is parallel to the rotation axis going in a north-south direction. The slowest direction is going perpendicular to the rotation axis, or east-west direction. The depth range is from 300 kilometers to pretty much the top of the inner core. Now, this model doesn't really explain what goes on right at the center of the Earth with a radius of about 300 kilometers. If you go there, the anisotropy is stronger, and the directions of fast and slow speeds are going to change. The fastest direction is still parallel to the rotation axis, north-south direction, but the slowest direction is no longer the east-west direction, but it's actually about 45 degrees from the rotation axis. So if you have a ray that's traveling in the diagonal sense, that's the ray that would come in late compared to other waves. So the Earth's inner core was discovered in 2002. And if you think about the Earth's inner core being discovered in 1936, it took us a long time to find this small thing. And the reason is simple. It's so small. And it's so far away from us that we needed to have a lot of data to say anything about this tiny kernel sitting at the center of the Earth. It's about 300 kilometer radius, so it's tiny, even in comparison to the inner core itself. In terms of the Earth's entire volume, it's less than 1%. It's 0.01% of the Earth's volume, and this makes it hard to find. It's hard to get a lot of data for this, but fortunately, with all the efforts put in by seismologists and governments to put in these instruments, we have a lot of data now to start studying these innermost inner core. And the other thing that distinguishes the innermost inner core is that this is the change in anisotropy that makes us find it, not change in composition or change in phase. It's actually the change in anisotropy that we didn't really think about back then when the inner core was discovered. Now, the anisotropy is a little bit unfamiliar. We're not used to seeing anisotropy all over the place. So let me try to explain one case how the anisotropy can develop in the inner core. If you take a single crystal of anything, any material that makes up the Earth, it turns out a single crystal is typically anisotropic. It has the direction in which the waves would travel in a with fast speed, and it would typically have a slow direction. That's a work of mineral physicists. They can take a rock, measure what the direction, wave speeds in different directions are. Now, as seismologists, we're not seeing single crystals. What we are seeing are the bulk properties. So these crystals have to be put together. If they're put together in a random fashion, the fast direction would be pointing all over the place, and same thing with the slow direction. The bulk property that we would measure in terms of what the rock property is, and that's what we measure with seismic waves, is isotropic. In other words, there's no dependence on direction. Whichever direction I go, I'm going to sample both fast and slow directions, and therefore I'm going to average out. That's the isotropic wave speed. However, if there is some sort of mechanism that would align these crystals, that's a different story. You could end up with the bulk property that would preserve most or some of the anisotropy that's expressed by a single crystal. The easiest case is if you grow the single crystal to a large size, then the bulk property would still have anisotropy in there, and that's what we can measure in seismology. So in order to interpret what we observe in terms of seismic wave anisotropy, we need to know what these are, what the mineral physicists can tell us in terms of what the composition of the inner core is and how they behave in terms of seismic wave speed. So let me focus on this. Now, we know that Earth's inner core is roughly made up of iron with some other things, but it's very difficult to measure them because we have very high temperature and high pressure. Somehow we have to get these material up to 6,000 degrees, which is, again, the temperature at the surface of the Earth, surface of the Sun. And we also have to squeeze them quite a bit in order to measure what these crystals are doing at the center of the Earth. And people have been working on that. There's a very famous paper from Francis Birch in 1952. He is very famous for determining what sort of material would make up the inside of the Earth. And in this paper, he describes what sort of candidates we have in the Earth. Now, this paper is famous for its scientific value, but it's also famous for a little bit of dictionary that he put at the end. So here's what happens at the end. Let me read it. Unwary readers should take warning that ordinary language undergoes modifications to a high-pressure form when applied to the interior of the Earth. A few examples of equivalence follow, and he gives a high-pressure form and an ordinary language form. If you have a high-pressure form, in other words, if you're reading these high-pressure mineral physics literature, and if you see a word certain, you should treat it as in ordinary meaning, dubious. If you see undoubtedly in the high-pressure form, that means perhaps. Positive proof means vague suggestion. Unanswerable argument means that trivial objection. And lastly, he says pure iron in high-pressure form. It means uncertain mixture of all elements. In other words, it's so hard that it's very difficult to do. Now, Birch back then had a lab, and this is how he was doing his experiments. He had a press, and he was basically squeezing material to measure what the seismic wave speeds and densities were. Now, this photo, I believe, is taken in early 1940s. We don't really have a date on it, but the publication seems to be around 1940. So that's the lab he had at Harvard in the basement of the museum building. If you've been to museum, this was in the museum basement. Now, we've made some progress since 1950. So the type of instrument that Birch was using was basically squeezing, and that's what we call pressure vessel. We basically squeeze with the cylinder the material to up to 4 to 6 gigapascals. And that gets us down to some depth. It gets us down to about 100 or 200 kilometers below us. But again, the Earth's radius is much larger than that, so we'd like to go further. Now, another option is to use diamonds. If you have diamonds, 2 diamonds, or multiple diamonds, and you have tiny sample between these two, we can actually squeeze them very well and get up to about 300 gigapascals. That would get us kind of into the inner core. Not quite to the center of the Earth, and people are working on that to increase that. But we can definitely get up to the inner core sort of thing. We can also do shockwave experiments. This is where you have a huge gun, and you shoot a projectile towards your sample, and this hits and instantaneously produce very high pressures. This would take you up to as high as 50 terapascals. This is way beyond the Earth's center. This is the central pressures of giant stars and things like that. So this is a little overkill, but we can definitely do things at the inner core pressures and temperature. These are experiments that we can do and have been doing in terms of trying to measure the seismic properties and density of the material inside the Earth. There's also another invention, computers. We can now start to do simulations of atoms at these temperatures and pressures and try to come up with an estimates of seismic wave speed and density. So here's one simulation where you're looking at temperature of nearly 5,000 Kelvin, pressures of 312 Kelvin. And we're basically solving the Schrödinger's equation and seeing the interaction of the atoms with one another. This is a case where we are looking at pure iron. So each of these yellow circles or spheres are iron atoms, and you can see that they vibrate. And that's what we can actually average out to get the seismic wave speed. The nice thing about computer simulations is that we can change things easily. I can add a little bit of silicon, so the blue spheres are the silicon atoms. And we can do the same sort of simulation at high pressures and temperatures, and we can increase the temperature and pressure fairly easily to model what happens. And you can see immediately that as soon as I put in silicon, a small amount of silicon, the motion is very different. The iron wasn't moving very much, so let me try to, it's not going to start again. But iron wasn't moving very much, but silicon made it softer. Things are moving more. So it's going to make differences in terms of seismic wave speed. We can also determine the density, and also come up with the measurement of the wave speed as well as anisotropy. Here's one example of seismic wave speed on the y-axis and angle from some direction. So we can see that the seismic wave speed is slowest when it's 45 degrees. Very similar to what we observe in terms of the innermost inner core, and it's fastest when it's going north-south. So what we can start to do, what we can hope to do, is to start using this sort of constraint from mineral physics, both experiments and theoretical calculations, with what we observe from seismology. So here's one possible case. We have constraint on what the crystal structure is here. We can compare the prediction of travel time residual, which is shown by this blue curve, with what we observe. So this is the case of the innermost inner core. See this bending shape that was specific to the center of the Earth? We can compare them, and if they agree very well, we can say that, okay, the innermost inner core seems to have nearly perfect alignment of crystals. In other words, it's acting like a single crystal. Now, we can take the same material and ask the question of, well, we have a bulk inner core which has different sort of anisotropy. The magnitude is smaller, it's weaker anisotropy, and the directions are different. Assuming that we have to use the same material, can we come up with some sort of alignment distribution that would explain what we are observing in terms of the bulk inner core? And this is something that we are working on with the mineral physicists. And it's going to give us an idea of what happened as the inner core grew, and if there are any effects in the Earth magnetic field and things like that. So we can compare the Earth seismic observations, the bulk versus innermost inner core. First thing we have to come up with is composition. So we know that it's mostly iron, but the question is, what is this others? It's better than how Francis Birch put it. It's not a mixture of all the elements, but we certainly have a lot of candidates to try out. Now, that composition has to match with seismic observations, so we have some constraint, some potential candidates, and what we do is we do the mineral physics experiments or calculations to try to match them. Once we can find the composition, we might be able to do something like this. We can start to ask the question of what is the alignment? Why is the innermost inner core different from the bulk inner core? It might be that the alignment is different. The innermost inner core is acting like a single crystal, whereas the bulk of the inner core has a mixture of directions that would reduce the anisotropy to a lower value, as well as changing the direction of fast and slow if you have specific alignment distribution. So in summary, I've taken you from the surface of the Earth to the center of the Earth. And the center, I think, is very exciting because we are dealing with a lot of technologies that have been developed. We have a lot of observations. We are continuing to increase the observations, and therefore we'll have more and more constraints to play around with. So in summary, we have the Earth interior, which is high pressure and temperature, so high that we really can't send anything down there beyond the top part of the crust. There's not much we can do. So we have to rely upon non-invasive techniques to image the interior of the Earth, and one very popular way is to utilize the seismic waves that go through. And we know that based upon those seismic waves that went through the Earth, we know that there's a mantle, there's an outer core, and there's an inner core. The mantle is made up mostly of rocky material, lighter material that floated on top of metallic core. And there's convection going on. Even though it's solid, it has very sluggish convection that drives the plate tectonics that we observe at the surface of the Earth. The outer core is also convecting. It's a more vigorous convection than the mantle. Part of the reason is it's liquid. It has low viscosity, so it can convect very easily. And this is the place where the Earth magnetic field is generated. That's the one that shields us from harmful solar radiation. Below that, we have solid inner core. The material should be about the same, but we go from water to ice or outer core to the inner core. And this is where we observe anisotropy. This is not something that we observe typically in the mantle or the outer core, but anisotropy definitely is a factor that we have to consider if we want to learn about the inner core. The anisotropy seems to make a distinction between the bulk part of the inner core and the central part of the inner core, and we call that innermost inner core. We don't really know why the difference is, so we have to rely upon constraints from mineral physicists to learn about why the innermost inner core is behaving differently from the rest of the Earth. And this is where things get really exciting, because I start to talk to mineral physicists, geodynamicists, and this is going to be a multidisciplinary study to really understand what goes on inside the Earth and how the Earth evolved throughout Earth history. Thank you.